is here, DC load line. Here, the DC load line is drawn on the output characteristics of your common emitter configuration. Now here, this graph shows the output characteristics of your common emitter configuration. Now here, if you want to draw a line, here is saying that DC load line. That means if you want to draw a line, compulsory require 2 points on the graph. Here, this is the output characteristics of your common emitter configuration. Now, if you want to draw this line, if you want to draw this, compulsory require 1 point on the y-axis as well as 1 point on the x-axis. Okay. Now I am going to determine those 2 points on the x-axis as well as y-axis and determine those 2 points. How to determine those 2 points? These points are determined by taking the output equation of your common emitter configuration. Okay, here I am going to take the common emitter configuration equation here. Here, this equation shows the common emitter configuration output equation. VCC is equal to ICRC plus VCE. Here, this is the output characteristics of your common emitter configuration. Okay, now this is the equation related to that common emitter configuration. Output equation. This is not the input equation. This is output equation. Why? Because we are going to draw the DC load line on the output characteristics of your common emitter configuration. So that's why I'm going to take the output equation of your common emitter configuration, and the equation is given by VCC is equal to ICRC plus VCE. Okay. Now, in first case, keep this VCE is equal to 0. Here, if you keep this VCE is equal to 0, then you are going to get the point on this y-axis. Here, listen carefully. If you keep this voltage axis is equal to 0, then you are going to get 1 point on this y-axis, nothing but IC here. When VCE is equal to 0 from this equation, you are going to get IC is equal to VCC by RC. Okay. Now, keep this point on this. Assume this as point A. This is VCC by RC and this equation is VCC by RC. 1 second. Okay, this equation will become IC is equal to VCC by RC, and we are going to name it as point A. Similarly, if you want point on this x-axis, you have to keep y is equal to 0, nothing but IC is equal to 0 in this equation. Now here IC is equal to 0. Because of that, VCE is equal to VCC, and because of that, VCE is equal to VCC. I am naming that point as B. I am naming that point as B. Okay, here this is your point B and A. Okay, now we got 2 points on the x-axis as well as y-axis. Okay, if VC is equal to 0, IC is equal to VCC by RC. Now this point is 0, VCC by RC. Point A here, VCC 0, VCC by RC. Similarly, if IC is equal to 0, VC is equal to VCC. This is point B now. Now this is nothing but VCC, 0 here, VCC, 0. Now these two we got the points. Okay. Now, if you join this point A and point B, it will become the DC load line. Okay. Now, this is called your DC load line. Once I am repeating, here we are going to draw the DC load line on the common emitter configuration output characteristics. That means, if you want to draw this line, we require 1 point on the voltage axis, 1 point on the current axis. For that purpose, I am determining these 2 points by taking this output equation of your common emitter configuration and determining this A point and B point. After determining these 2 points on the x-axis and y-axis, if you join these 2 points, it is going to call it as DC load line. Okay. Now, here what is meant by this Q point? This is very, very important. This is major role in the case of DC load lines here. Q point. What is meaning of this Q point? Here, the Q point or the operating point, you can call it as quiescent point otherwise. Quiescent point or operating point is defined as it is the intersection point of your DC load line on the common emitter configuration output characteristics. Okay, once again I'm repeating. Here, the operating point or quiescent point is defined as it is the intersection point of DC load line and the common emitter configuration output characteristics. Okay. Now this is a quiescent point and this is also one more quiescent point. 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 These all are your quiescent points. Okay. Now see here. quiescent point is near to the saturation region, near to the cutoff region, exactly center of your DC load line, then what will happen to the output voltage or output current? See here, the left side of this graph is your saturation region. See here, left side of your graph is your saturation region, and this total blue color is your active region, and below of this is called your cutoff region. Okay, cutoff region, saturation region, and active region. Now here, I am taking this quiescent point. Now three conditions are there. That is, if quiescent point is near to the saturation region, near to the cutoff region, and exactly center of your DC load line, then what will happen to the output voltage? Okay, now for that I am going to take another slide. See here. Now here, now from this slide, if you observe this quiescent point near to the saturation region, here, if the quiescent point is near to the saturation region, then what will happen? Now here, quiescent point is near to the saturation. Sorry, you have to observe this graph. You have to observe this graph here. Now this point is near to the saturation region. That means this is an input waveform only. Okay, this is an input waveform. When you give the input waveform as like this, then what will happen to the output waveform? There is a distortion in the case of output waveform. That is, positive pulses are going to see here. We are missing this positive pulses here. We are missing this positive. This lines are there now. We are missing these pulses. We are not getting this output. We are getting the output as like this here. I'm drawing this here. Like this, we are getting the output. Like this. Like this, we are getting the output. That means we are missing this point. That means the output is not replica of your input. The output is not replica of your input. That means we are missing this much amount of output waveform. See here, I'm drawing this point. Now this is missing. This waveform is missing. That means the output is not replica of your input. If this quiescent point is near to the saturation region, the output is not replica of your input. That means there is a distortion in the case of output waveform. Similarly, the quiescent point is near to the cutoff region. If you observe here, now observe here, if the quiescent point is near to the cutoff region, then what will happen? Now this is an input waveform and this is an input waveform. When you give the input waveform as like this, then there is a distortion in the case of negative pulses here. These lines, observe these lines. Now there is a distortion in this negative half cycle. That means when the quiescent point is near to the cutoff region, also the output waveform is not replica of your not replica of your input waveform. That means there is a distortion in the case of output waveform. So that's why we won't connect the common base, common emitter, common cutter configurations in the cutoff region or in the saturation region. We won't connect the circuit in the saturation region or cutoff region. Why? Why? Because the output is distorted. The output waveform is distorted. That means there is a missing of pulses in the case of output waveform. The output waveform is not replica of your input waveform. So that's why we won't connect the circuit in the saturation or cutoff region. Then what will happen if you connect the circuit in the active region? Now here, if you observe here, if the quiescent point is center of your DC load line, see here. Now this is a DC load line. Now this is center of your DC load line. Quiescent point is center of your DC load line. Otherwise, in the active region here, quiescent point is that active region. Then what will happen here? Now this is an input waveform. Now we are going to get the output waveform as exactly replica of your input waveform. That means there is no distortion in the case of output waveform. We are going to get the exact replica of your input waveform. So that's why we are going to connect the circuit in the active region. Otherwise, we have to maintain the quiescent point in the center of your DC load line. Okay. The quiescent point must be in the center of your DC load line. Otherwise, the quiescent point, if it is in saturation region, if it is in cutoff region, the output is distorted. Why it is distorted here? In this case, cutoff region, both are connected in reverse bias now. That means there is no negative pulses. Okay, here there is a missing of your pulses. Okay, like this, we are not going to get the output waveform similar to input waveform. There is a discussion. Okay. Now here, compulsory you have to maintain the quiescent point in the center of your DC load line, otherwise active region. Okay, this is about your DC load line.